and y. Now, these three forms of representations are equivalent, and you will see them used interchangeably, even during this presentation or any other text that you'll be looking at relative that tries to speak about first order differential equations. Now, typically, when you want to solve a first order differential equation, we would expect that we have an exact solution to those equations. However, that is not always the case. Some differential equations are much more difficult to solve, and in that case, we resort to other means, such as an approximate solution using numerical methods, such as Euler's method or Runge-Kutta's method. Now, we'll start off with Euler's method. Euler essentially developed a method for solving first-order initial value problems. Now, I talked earlier about what first-order equations are. I think then I'll just briefly explain what initial value problems are. Initial value problems are essentially problems whose initial values have been given. So it means that there's a start-off value that we have, typically either called your x naught or y naught, explicitly stated as the initial value. Now, for us to go ahead to understand Euler's method, it will be good to set some notations in place. To start with, we will be using the first order representation of a function y prime or dy dx equals to a function of x and y. And we would also be using the notation y of x naught equals to y naught, where x naught is our initial value of x and the y naught is our initial value of y. Now, our goal here is to find a numerical solution. We want to find a set of points that would lie along our initial value problem. Now, the graph you see to your right shows the only point that we know currently prior to even trying to solve the differential equation, which is the initial value or the initial condition. So now we know that we know one point given. We know a point and we know the x-axis, the x value of that particular point, and we know the y value of that given point. Now, looking at the graph on display here, you're going to see a blue curve. Let me see if I can get a pointer. You're going to see this blue curve here. Now, what we would use this curve to do in the presentation is to show what we think the exact solution is. This is not, we don't know the exact solution, right? And that is why we're able to resort into Euler's method to get an approximation. But for the sake of understanding of Euler's method, we'll represent the exact solution as this blue curve. The only thing we know for certain is that the exact solution passes through the initial points that we have been given. Otherwise, this blue curve is just a representation of what we think the exact solution is, even though we do not know the true solution to the particular differential equation. Now, the question that arises is, how do we then get other points beyond this initial point that has been given to us? How do we get more points that we can then maybe sketch our own curve that is going to be an approximation of what the exact solution is? We need to find a way of generating more solution points in addition to the single points that we have. Now, if we go back to the initial equations I displayed earlier, you would notice that we stated two things. First, we said there's an initial value, and we also wrote the representation of the higher order equation. This graph only shows the use of the initial value, our x naught and our y naught. So now let's look at how we can incorporate the differential equation. Now, from prior knowledge of mathematics, we know that a slope, right, is the rate of change typically of a line, the rate of change of the y-axis relative to the x-axis. Now, the slope of a curve at a particular point, right, it typically speaks to the rate of change of one variable with respect to another variable. Now, dy dx in itself, the first order differential, also measures the rate of change of y with respect to x. We will see that these two things, the slope of the curve and the y dx, are similar. As such, you would see typically that they say even the slope of the curve is equal to the first differential, which is also a representation of a function of x and y, which is essentially the rate of change of y with respect to x. So now going forward, we'll represent the slope of the solution as a function of x and y. And that's because a slope measures the rate of change of one value with respect to another, and your dy dx or your differential also measures the rate of change of y with respect to x. We'll see that these two things correlate. As such, typically they are equated to one another. Now, since we have spoken about the slope, the question is, how does the slope even matter? Or how are we even going to use this slope to get other points that we're looking for? Now, the graph you see here on the other hand shows the slope at the point x naught and y naught. The slope is represented with the red line on the graph. Now, typically we get the slope by substituting the value of x and y. We already said that the slope of the solution at point x naught and y naught is a function of x naught and y naught, right? And this means that the point itself definitely should lie on the exact solution of that particular equation, or at least the initial values that we have provided. Now, since we know that, we can then use this to then get subsequent points on the graph. And what we essentially do is try to build tangents incrementally and see how this will get us so close to the exact solution. Remember, I said initially that this blue curve you see there is unknown. We're just using it as a representation, and we want to understand how Euler is going to deduce an approximation relatively close to the exact solution of the equation. Now, if you look at the picture, if you compare the exact solution, which is represented by the blue curve, to our tangent line that we have drawn, you will notice that even though they don't follow the exact same path, they are not necessarily far apart. That would suggest to us that maybe this tangent line is an approximation, and that would just be our best bet in getting something relatively close to the exact solution. Now let us assume we move a short distance away from our x naught, which is the initial value that we have been provided, to a point x1. We can then locate the corresponding value of our y1, which is here. And it's going to look like this. Now we'll still see that at point x naught, at point x naught, y naught, we are on the exact solution. But at point x1, y1, we have started our approximations and we are relatively close to what we need. Now our new point x1, y1 is not necessarily far away from our true solution. And at this point, we know two values of the solution of our differential equation. The first value is the exact value, which was provided as our initial condition. And the second value is our x1, y1, which is an approximate value and lies on the tangent to the initial value that has been provided. Now, the movement we made from x1 to x0, to x1 is typically called the step size. And we'll see how the step size is used going forward and how it even affects the solution to our differential equation when we look at other parts of the presentation. Now, at this point, we have our x1, but then it doesn't stop there. We want to get several points because we want to have a curve that is as similar to the exact solution as possible. What do? At our point x1, y1, we then get the slope right, of a tangent is typically referred to the tangent because it's not necessarily an existing tangent, right? We get the slope at that point at x1, y1. And essentially it means that since we have established earlier that the slope of the solution is a function of x and y, so the slope at our point x1, y1 will be a function of our x1 and y1. The first diagram here shows the slope drawn at that particular point. And the second diagram is a repetition of the procedure we had done initially. We take another step to the right on the x-axis. When we take the step to the right, we trace the x coordinates to the point, and we also trace the y coordinates to that point. Essentially, we're locating the corresponding points on the pseudo-tangents that we have already drawn.
Yeah, hello.
So I can hear you.
All right. I think probably you need to throw more light on your, you have the blue line or the purple line on your red line. Now, if you look at your x naught, there was a straight line in the previous slide. There was a straight line going upwards, which is at variance with the blue line. It seems to be a little far away from the blue line, right? That means you said you got the slope of x naught and x1. Then you went further to get the slope of x naught and x1, right? You got the slope again. The line shifted closer back to x2, to that purple or blue line. How do you get that shift where the line became straight instead of it became slanty instead of straight, as it were? How do you calculate that slope?
So the slope here is at the point x naught and y naught. That's the slope you are seeing here, not at the point x1, because it's the slope at our initial value. The line is just extended. So this line you are seeing here is the slope at our point x naught and y naught, right? What we did here is to then get our slope at point x1 and y1. Since these are different points. How did you
calculate the slope, please?
The slope will be a function of our, like it's going to depend on the differential, on the equation you're working on. F of x of y is going to be a first order differential equation that you have been provided with. What you will do is replace the x naught in that particular equation with values x1 and y1, and that will give you the slope at that point.
Okay.
So the next thing we do the same thing and calculate for at the point x2. We also find our slope at that point, replacing the values of x1 with values x2 and y2. So this process is essentially going to be a repetition, and we'll see that the lines keep getting joined together. Now this is also repeating the same process again, but then I take another step to the right from my x2 to x3 and also calculate the slope at that point. At this point, we'll see that we have values x0, x1, x2, and x3. We would also notice that as we keep stepping, we can see that it looks like the solution starts to diverge away from the exact solution. But since this is an approximation, right, this may just be our best bet, as we cannot even determine the exact solution. And this curve is just a representation of what we think that exact solution is. Now, my other colleague will speak more to stability of this kind of solutions and convergence when he takes his part of the presentation. So this essentially is a basic introduction to Euler's method. And this is going to set a precedence for us to even understand how Euler deduced the formulas we're going to be using going forward. Any questions at this point?
Is it Euler or Euler?
Yeah, it's pronounced Euler.
Okay. At least I've been in school for how many years now? I think almost 22 years or so. It is Euler that I know, not Euler. All right.
Okay, so we're going to look at the derivation of Euler's formula. I'm sure I think this graph to the right, we should have some level of familiarity with this graph to the right, even though this is just like a truncation of that particular graph. The blue line still represents our supposed exact solution. Our xn and our yn are initial value. They are corresponding x values and y values for our known points. The initial values are always given. It's required for Euler's formula, because Euler's formula it solves initial value problems, and those initial values have to be provided. Now for our new point, let's represent our new point as x of n plus 1. Since we're taking one step to the right, and we represent our y-axis as y of n plus 1. Now the difference between our x of n and our x of n plus 1 is what we call our step size. And that essentially means how long did we step to the right. In this presentation, it will be represented as h. So h is your step size, while the difference between y of n plus 1 and y of n will be represented as change in y or delta y, which is just essentially whatever change happened on the x-axis. Now, to determine the value of xn plus 1, from this graph, I think it is a bit straightforward. Our x of n plus 1 is essentially the addition of our x of n and our h. And that is what you can see in equation 1 here. So when we took a step to the right, so x of n plus 1, it is just an addition of x of n plus h. So it means that if I wanted to find x1, it would be x0 plus h. If I wanted to find x2, it would be x1 plus h. And I mean, depending on whatever point I'm trying to find, or what point I'm trying to approximate. Now, from our algebra, we know that our slope here is represented as, some people just say rise over run, or your change in y-axis over your change in x-axis between the 2 points that you have selected. So our slope here, which I had mentioned, is a function of x and y, depending on the given point you are using, is going to be our change in y over our h, which is equation 2 that is given here. If we make our change in y the subject of the formula, we will see that our change in y is the product of our h, which is our step size, and the function of x and y. But what we're really looking for here is y of n plus 1. We want to know the new value of y after we have taken that step. So now y of n plus 1, also from this graph.
Hello.
Sir?
Yeah, the x that's on your equation 3. Now you have delta y to be step sign function of x of n, y of n. Is it a subscript?
Yes,
or
that should be a
right
subscript.
beside?
Sorry. No, it's a subscript. That's an
And
error.
I think that should be corrected.
It will. I'll correct it after the presentation. So I was saying that our y of n plus 1 is also going to be our y of n plus our delta y, or change in y, which is represented here as equation 4. Now, if we take our delta y, which we have deduced from equation 3, and replace it in the formula for equation 4, we would notice that our y of n plus 1 equals to our y of n plus the product of our h, our step size, and the function f of x of n and y of n. Equations 1 and 5 are the basic Euler's formula that we'll come across. Those are the two equations that we'll be using to generate the next values as we step through and try to get our approximations. So now let's look at an example and see how these formulas are applied. The first example here says we should find 3 approximations, y1, y2, y3, using Euler's method for the initial value problem y prime equals to 1 plus y, where our y of 0 equals to 1 with a step size of 0.1. Now we have established earlier that typically our initial values come in the form y of x0 equals to y0. So from this y of 0 equals to 1, we can say our x naught is 0 and our y naught is 1. So the initial value of our x naught is 0 and the initial value of our y naught is 1. Since we are tasked with finding y1, y2, and y3, that suggests we would also need the values of x1, x2, and x3. From the formula we had derived earlier, x of n plus 1 equals to x of n plus h. Our x1 is our x naught plus h, and that's just 0 plus 0.1. We have 0.1. Our x2 is 0.2, similar to the way we deduced x1, and our x3 is 0.3. Now, taking the formula to deduce the y points of our solution, we take the Euler's formula we had also deduced earlier. I say our y1 is y naught plus h, f x and f of x and f of y. Now, the function here is represented as 1 plus y. So we'll just take that function and replace it here as 1 plus y naught in this case. So you replace your y naught, which has been given as 1, we have 1 plus 1, and we get 1.2 as our y1. We do the same thing for y2. Our y2 is y1 plus h into 1 plus y1, and we get the value for our y2 as 1.42. We do the same for y3, and we get the value of our y3. If we do the calculations here, just replace the values of h, y2, we get our y3 as 1.662. And that means that the first three approximations, or the y values for our first three approximations are 1.2, 1.42, and 1.662. Any questions? No, okay, so I'll move forward. This is a second example, which is slightly different from the first example. Now here we are giving the equation as dy dx. Remember I said the equation can either come as dy dx or y prime, typically used interchangeably. Our dy dx here is 3x minus 2y. We have our initial condition given as y of 0 equals to k. K is a value that we need to determine. Then the Euler's method here says we have a step size of 1, and they have given us the value of the approximation at y2 equals to 4.5. Now we need to find the value of k. Going from the question, we'll notice that our x naught is 0 here, and our y naught is k, a value we don't know yet. However, we know our y, we know y, yeah, we know our y2, which is 4.5. Now our x, and we get the value, we'll start with getting our value for x1. Our x1 is x naught plus h, which is 0 plus 1, which is 1. Our x2, also just replacing the values in the equation, is 2. Now we try to get our y1. Our y1 is going to be y naught plus h, the function of x of n and y of n. Now replacing h here as 1, we're provided with a step size of 1. Now we have 3x naught minus 2y naught. Our x naught is provided as 0, but remember our y naught is not given. Our y naught is represented as k, which is what we are trying to deduce. If we solve this further, we'll see that we get k plus 1 minus 2k. 3 times 0 is 0, and what is left is minus 2k. Now we have k minus 2k, which gives you minus k. Now our y1 is minus k. Now our y2 on the other hand, which is y1 plus h of 3x1 minus 2y1, we replace the value of x1 as 1, and we replace the value of y1 that we have deduced here as minus k, we replace it into the equation. We'll see that we have minus k plus 3 plus 2k. Now our y2 is 3 plus k. But remember, we have been given our y2 earlier as 4.5. So since our y2 is 3 plus k, and we are trying to determine the value of k, we equate 3 plus k to 4.5. When we make k the subject of the formula, our k is 4.5 minus 3, which is 1.5. Therefore, the value of k is 1.5. Now I'll be moving on to the Runge-Kutta's method. The Runge-Kutta's method tries to solve a deficiency that exists with the Euler's method. One problem with the Euler's method is the larger your step size, the more your approximate solution diverges away from the exact solution. So for Euler's method, you need to use like really small intervals to get something that is reasonably accurate, which may not necessarily be efficient. Now, Runge-Kutta's method is an effective and widely used method for solving initial value problems. Now, those methods are a general class of algorithms, and we'll be focusing on the fourth order method, which is the most popular one. The Runge-Kutta method is more computationally heavy and typically done with computers, right? In attempt to overcome the problems of the Euler method. But Runge-Kutta's method provides more accurate solutions when we compare it to the Euler's method. Now, for the sake of this presentation, I would not be talking through the derivation of the Runge-Kutta's method because derivation itself was quite complex to even I think to prove, and it was going to take like a very large chunk of the presentation. But then I think the equation for the Runge-Kutta's method is based off Taylor series and is represented as our y. The y values of our approximation is represented as our y of I plus 1 is our y of I plus 1/6 of our k1 plus 2k2 plus 2k3 plus 2k4 multiplied by the step size. Now, even the values for k1, k2, k3, and k4 are further represented as k1 is a function of xi and yi. K2 is a function of xi plus half of the step size, and yi plus half of k1h. K3 is also represented here, and K4 is also written here as a function of xi plus h and yi plus k3 of h. Now, for our K1, it's sort of easy to understand this because it's still similar to, the Euler's prediction, where we just use the function of xi and yi. But then for the values of K2, K3, it tries to estimate it tries to create an estimation at the midpoint to provide the higher level of accuracy when we compare it to the Euler's method. Now, the K3 also does the same thing. It takes smaller approximation because it tries to use the midpoint values. And then the K4 is sort of the extreme, like the end of the prediction. But for the x values, it's similar to Euler's method. It's just your x of y plus 1 equals x of I plus h. So I'll take only one example for the Runge-Kutta's method. Now the example here says we should find our y at 0.2 for y prime equals to x minus y over 2. Our y of 0 equals to 1. Our step length is 0.1. Now, given our equation y prime equals to x minus y over 2, our step size is 0.2. Our initial condition, x naught is 0. X naught here is 0, and our y naught is 1. The first thing we do is, based on this formula, we try to deduce our K1, our K2, our K3, our K4. Once we are done deducing it, we then insert it back into this Runge-Kutta's method written here. Runge-Kutta's formula, sorry, written here. So our K1 is our step size multiplied by a function of x naught and y naught. We just take this function that has been provided here, replace the values of x naught and y naught in this particular function, and multiply by our step size. For our K1, we get minus 0.05. Our K2, on the other hand, also taking the Runge-Kutta formula for K2, is our step size multiplied by a function of x naught plus the midpoint of our step size and y naught plus K1 that we have deduced earlier over 2. We also replace these values in the formula x minus y over 2, and we multiply it by the step size to get our value of K2. We do the same thing for K3, and we deduce the value of our K3. Then we do the same thing for our K4, and we deduce the value of our K4 by also replacing these values in the function that's been provided here and multiplying it by our step size. When we have determined the values of K1, K2, K3, and K4, we then replace it in the Runge-Kutta's method here. And when we replace it, also, replace all necessary values. We know what our Y naught is 1. We have gotten our K1, our K2, K3, and K4. And we also replace those accordingly. And when we deduce this, so the first time we step, which is, remember our step length is 0.1. So the first time we take a step, right, we have stepped by 0.1. Our value of Y is 0.95369. Now, this is just the first time we're taking a step. They want us to calculate after stepping twice. So it means we still need to calculate the value of Y2. Now we're going to just essentially repeat the process here. The process we had done here earlier, but instead of using our X0, we'll be using our X1 and our Y1 respectively. We'll find the values of our K1. We'll find the values of our K2, we'll find the values of our K3 and our K4. After we have deduced all those values and essentially just replacing the X1 and Y1 values in the equation, and also doing the same replacement for our K2, K3, and K4. Now, once we are done with this, and we have deduced the values of K1, K2, K3, and K4, similar to what we did when we took a step the first time, I'm going to replace the value in this Runge-Kutta's method. And then, also replace Y1 that we have also determined from the first step that we took, which was 0.95369. We're going to do this computation and we'll get our value at Y2. Our value at Y2 is when we took the step the second time, which is 0.91451. Like I mentioned earlier, Runge-Kutta's method when compared to Euler's method is computationally heavy. And typically you have like programs such as MATLAB that are written to use or apply this particular method. But then when compared to Euler's method, it is much more accurate and the approximations are typically much more closer to the exact solution. If no one has any question, I would pass it on to my colleague Moses to talk about the multi-step method and the predictor-corrector formula.
Sorry, I was hoping that you would go over this Runge-Kutta method, how to derive the Y naught again, please. I said, can you please go over how you got the Y naught for the first iteration? That's the first step, please. Yes, this place exactly.
Okay, which
the value
Y naught?
Yes.
This value of Y naught here.
Yes.
Oh yeah, the value of Y naught is our initial condition. Remember, like I mentioned earlier, that when you see equations of this from Y of 0 equals to 1, right? Yes. This 0 here is our initial condition for X, which is X naught.
Okay.
Yes, so this one here is the initial condition for Y, which is Y naught. So I didn't necessarily deduce anything. I just replaced the values given in the question. So our initial condition for X here, maybe I'll write it more explicitly. But then the X naught here is 0.
Okay. Because after the fourth, when you wrote fourth order, okay, that's comma. I thought it was 0.1 again.
Oh, no, it's 0. Oh, okay, I see the confusion. It's 0.1. So it means that I'll be replacing the values of 0 and 1 in this equation here. So it will be 0 minus 1 over 2. And that would be like minus 1 over 2. That would be minus 0.5. I'll then multiply it with 0.1 to get minus 0.05.
Okay, thank you.
So Moses, let's take it away.
Okay, thank you, Miriam. Good afternoon, everyone. Good afternoon, sir. My name is Moses. I'll be talking about the multi-step method and the predictor and corrector formula. So basically, this is just a next iteration of what Miriam has been saying, because multi-step is just all about just computing using the past values, unlike Euler and Runge-Kutta, that are called single step, because what they do basically is just to use a past value to compute the next value. But multi-step just take account of the accumulated previous value to compute the next value. So the methods of Euler and Runge Kutta are called single-step methods or one-step method because they use only the information from one previous point to compute the successive points. That is, the initial point x naught, y naught is used to compute x1, y1. And in general, yk is needed to compute yk plus 1. So what this is just saying is what I said earlier, like single-step method like Euler and Runge Kutta. What they just do, they use the previous points to compute the next point. But here in multi-step, what we'll be doing is to use a collective of previous point of x and y simultaneously to compute the next step. After several points have been found, it is feasible to use several parallel points in the calculation. Methods that use information at more than the last merge point are referred to as the multi-step method, like what I said earlier. More precisely, a method is called a multi-step case step if the computation of the next approximate solution yn plus 1 is based on the last approximate solutions. So like what I've been saying earlier, we can just say yn plus 1 and f1 are just the same thing. But like in some formulas or in some articles, you might see yn plus 1 as relating to the present value that is being approximated from the past values, or you can see f1 that just saying the same thing, that just the same, basically the same representation. So we can denote our past values with f minus 1 or y minus 1 or f minus 2 or y minus 2. So basically, what all these are just denoting are just our past approximate solutions that we've derived through solving. Miriam, can you go to the next slide? So multi-step methods are used for the numerical solution of ordinary differential equations. Conceptually, a numerical method starts from an initial point and then takes a short step forward in time to find the next solution point. So basically, multi-step is not really the approximate solution in itself. It's just a means of solving the problem. Just like the way single steps is not the solution itself, is the likes of Euler and Runge Kutta that the approximate solution, but they are just classified as a single step because of the approach of solving the problem. Just like what we are doing here now, like part of the families of the multi-steps method, which I'll be talking about in the subsequent slides, are the predictor and the corrector formula. So all that take cognizance of the previous past values and solving them simultaneously in getting our next initial points. So the process continues with subsequent steps to map out the solution. Single step methods such as Euler refer to only one previous point and its derivative to determine the current value, like what I've been saying earlier. This is just the summary of the difference between single step and multi-step is that single step just use the previous value, the previous point to determine the current value, while the multi-step use is the subsequent previous steps. Like we're not going to just only have one previous point, we're going to have more than a previous point. And we now solve all these previous points simultaneously in determining our current approximation solution for the current value. So Miriam, can you go to the next slide? Thank you. So using the combination of a predictor and corrector method requires only two slope function valuations. The predictor-corrector forms are among the most efficient known integration methods in terms of speed and accuracy. As a class of integration methods, the multi-step sets are among the best, but individually as a predictor-corrector set, the best choice for the best method varies depending on the application. Like what we've been discussing for the past weeks is just all about approximation of a solution, so not the exact solution. And what this method just does is that they just offer the best way of approaching and solving a problem. Like what multi-step does now is that it takes cognizance of the previous past values, not just only one initial point, the other initial point to derive the next initial point. And what this does that it makes our approximate solution after solving to be more closer to the exact solution. Miriam, please can you go to the next slide? So now we're in the predictor and corrector methods. So in numerical analysis, predictor and corrector method belongs to a class of algorithms designed to integrate ordinary differential equations to find an unknown function that satisfy a given differential equation. So like what this is just saying is that if like in a predictor and corrector question now, they're going to be given a condition, because even though you know the formula offhand and you insert correctly and everything, but if you don't follow the condition that was given in the question, even though if you compute the formula correctly, your answer is going to be 100% wrong. So you have to take cognizance of the condition that is given in each question when solving, because that's the key in getting the right values to insert in the formula. So the initial prediction step starts from a point fitted to the function values and derivative values at a preceding set of points, like what I've been saying earlier, like preceding set of points, like some other previous points is going to be given also in the question. So we are going to be solving simultaneously. What I mean by simultaneous is not simultaneous equation, like we'll be using those previous value all together at the same time to solve for the next point. So what the corrector does is that it takes the predictor value, then after solving with the condition that is given in the question, it computes in the formula. So we now insert the formula, and it now refines the initial approximation that has been given by our predictor's formula. So let me just explain very well now. So the predictor and the corrector methods are two separate formulas, but they work together. Firstly, you're going to use the predictor formula to get a value. Then after getting a value, after the insertion into your formula and getting the value, they are going to insert your condition that's going to be given the question. Every question has to have a condition that tells you how to compute the value of x and y. So after inserting successfully to your condition, you're now going to insert that value back to your corrector's formula to now get the final predicted value, which is going to be close to the exact solution. So Miriam, please can you go to the next slide? So please, sorry for the handwriting. I had to just make it very big so it's going to be legible to see and all for visuals. Yeah. So the predictor formula is also known as the Adams-Bashforth formula, because that's the man behind the formula, Adams-Bashforth. So it's also known as the Adams-Bashforth formula. So like what I was saying earlier now, if you look at our predictor's formula now, you can see y1p is equals to y0 plus h divided by 24 bracket 55 f0 minus 55 f minus 1 plus 37 f minus 2 minus 9 f minus 3. So the value of y0 at the initial point is always 1, while the value of x at the initial point is always 0. Why h is our step size, just like what Miriam has been talking earlier. And in some questions, you might be given the step size, while in some questions, you might only be given the value of the x. So you can just deduce the value of your h by looking at the difference in the increments of the value of your x, of your past x values, because the value of your past x values increases the same way proportionally from one past value to another. So for example, it starts from 0, then it goes to 0.1, then the next past value 0.2, 0.3, and all that. So now the difference of the movement from one point to another point, that's your step size. So in some questions, you'll be giving your step size, while in some questions, you have to deduce it yourself. So now, if you now look at our correctors formula now, so likewise, we have y prime c is equals to y naught plus h. No, sorry, y1 c is equals to y naught plus h divided by 24 brackets 9 f1 of p. So you can notice that this f1 of p now, to get this f1 of p now, is through our predictors formula. Because after getting our y1 of p, so the condition given in our question, so we're going to insert this value of y at that point of x and solve for f1 of p. So in our subsequent slides, when you start seeing an example, you start understanding what I've been saying. So we now have plus 19 f naught minus 5 f minus 2 plus f minus 2 brackets. So after solving for all this using this formula, you get your final approximated value, which is not really the exact solution, but more closer to the solution. So Miriam, please can you go to the next slide? So now we're given a question now, and the question here is that we are given a condition, and the condition is that f is a function of x and y, divide the x is equals to xy divided by 2. So that's the condition I've been talking about earlier. So now we're not giving the past values. So this is just the difference now between multi-step and single step. Single step, you don't get more than one past value at a time. But in multi-step, you get more than one value at a time to compute in your solution for your solution. So now you can see what I was saying earlier about our step. Like now, we're not giving our h, which is our step size. But now, from this value that we're giving now, you can notice that the value of x is increasing proportionally, like from 0, which at the initial point is always 0, and at the initial point of y is always 1. So from our x now, you can see that x is increasing proportionally. So the proportional increase now is now our step size, if we are not giving. So it's now our step size. So from now, you can now say that, okay, and the question is now that if you find y at the point where x is 0.4. So now, like what I was saying earlier, like after using our predictors formula to solve, then we're going to insert the value and follow the condition given. But before going that, there's still a lot of work to be done. So now, from these values here, we can now say that, okay, our past values to insert to our formula is, we can say that, oh, sorry, I forgot to denote. I'll correct this after this presentation. The value of x at 0 is meant to be x minus 3, while the value as x at 0.1 is meant to be x minus 2. Please, you guys should forgive me for this mistake. So the value at x is equals to 0 is x minus 3, which is a past value, the initial value, while the value at x is equals to 0.1 is equals to x minus 2. Likewise, at 0.2 is equals to x minus 1. At 0.3 is equals to x naught. So the value of our y2, like what I said earlier, 0 is x is...
Yeah.
Or,
excuse me,
yes, sir.
please.
Yes, sir.
Now, looking at the right-hand side,
Yes,
you have
sir.
x to be equal to 0, right?
Yes, sir.
Comma y minus 3. Is it
Yes,
a
sir.
subscript or y minus 3?
No, it's a subscript, sir. Sorry, sir.
Okay,
Sorry
but
for
you were
the handwriting.
making a correction just now, right?
Yes, sir.
That's x. Okay, let's look at the next step. X equals 0.1, comma.
Yes, sir.
Y minus 2 equals this. Is it x minus 2?
Subscript.
Because that's
No,
what you said in your...
sorry, sir. Pardon me, sir. It's also x subscript minus 2, sir. Not x minus 2.
Please go repeat.
Okay, sir. So for our initial point now, which is x is equals to 0, it's going to be x
Okay.
subscript minus 2. Y at the point of 0.1, which we were given, is going to be x. Sorry, sir. The initial point is going to be x minus 3 is equals x subscript minus 3 is equals to 0.
So it should be 3, not it should be x, not y.
Sir?
Because what I'm seeing is x equals 0, that's at that point, y
Yes, sir.
minus 3 equals 1, right?
Yes, sir.
Should
So at that
it
point
be
of
y
x,
minus 3 or x minus 3?
it should be y minus 3, but this x is what I'm correcting, sir. The x is meant to have a subscript of minus 3, sir, just like the y, sir. The x here, sir, is meant to have a subscript of minus 3, just like the y.
All right.
Yes,
all
sir.
right.
Yes, sir. Because it's denoting the past values. So just like our x is equal to 0.12, it's going to be x subscript minus 2 is equal to 0.1, then y subscript minus 2 is equal to 1.01. So what is just saying that at this point, past value of x is our past value of y also. So it's not these past values now that we're going to use to solve for our f minus 1, f minus 2, and f minus 3. And to solve for this, like what I've been saying earlier, that the most important thing to solve for, like to follow, is using the condition, because you might solve using the formula correctly and insert correctly, but if you get the condition wrongly, your answer is going to be 100% wrong, because there's no how you're not going to satisfy the condition and you expect to get the right answer. So now, to get our f1, f minus 1 now, can you go to the next slide, please, Miriam? Now, to get our f minus 3 now, so we have to follow the condition given, which is f is a function of x, y is equals to y dx is equals to x times y divided by 2. Now, at each point now, using the condition now, so to solve for your f minus 3 now, to solve for your f minus 3 now, so you're going to just insert your value of x, the past value of x, that's x subscript minus 3 and y subscript minus 3 divided by 2. So you know that what I said earlier, because the first initial point of x and y is of x is 0, while the initial point of y is always 1. So if you now insert to your formula and solve, you discover that at f minus 3 is equals to 0, because 0 times 1 divided by 2 is equals to 0. So you do likewise for the subsequent, to get the subsequent f values, like the f minus 2 values also. So you insert x subscript minus 2 and y subscript minus 2 also. So what I said earlier concerning our step size, which is our h, because the value of x always increase proportionally. So from 0 now, it's increased to 0.1, then the next value will be 0.2 and 0.3 and 0.4. So now get the value of y that we were given also, y minus 2. So if we decide the value of y minus 2, so that's 0.1 times 1.01 divided by 2. So we'll get the value of f minus 2 that we're going to be using in our formula. So the last, so it now means to get the two value of f minus 1 and f0, f naught.
Hello.
Yes, sir.
Can you see what is below f subscript 2? There's a line.
Yes, it's going to be in the next slide, sir.
Oh, I see.
Yes, sir. Miriam, please can you go to the next slide? So to get the value of f minus 1 now, you do likewise what we've been doing in the previous for the previous f values. So we insert our x subscript minus 1 times y subscript minus 1 divided by 2. Then we solve. So we get our value of f minus 1. So for the f naught, so we do likewise. So it's going to be x naught times y naught divided by 2. So when we solve, we get the value of our f naught. So with this now, so we've gotten a value of f minus 3, which is 0, f minus 2, which is 0.0505, f minus 1, which is 0.1022, and f naught, which is 0.1535. So with all this now, the next step is now to use our predictor formula just to insert to where f naught is, f minus 1 is, f minus 2 is, and f minus 3 is. When I'm just going to the next slide. Now, using the predictor formula, like you can see here now, this is the formula again that I wrote again. Now, f1 p is equals to y naught plus h divided by 24 bracket 55 f subscript 0 minus 59 f subscript minus 1 plus 37 f subscript minus 2 minus 9 f subscript minus 3. Now, like what I was saying earlier, like h is the, like we should note that our h here is the difference between the value of our x, the proportional increase, because in some questions it's going to be given, while some questions it's not going to be given. So we can now say that, so like now, like I wrote it here out, our previous value of x, which is 0, 0.1, 0.2, 0.3. So you can see that the proportional increase is 0.1. So we're always going to give our value of x most of the time, but most of the time our value of h should not be given. So to get a value of h, we just look at the proportional increase of x, which for this case is 0.1. So what we just have to do here is just to insert and solve. Insert our y naught that was given in the question, insert our step size 0.1 divided by 24, then insert, then brackets, the under bracket 55 times the value of f naught, f subscript 0 that we solved using the condition given in the question in the previous slides. So after inserting for f, for f subscript minus 1, f subscript minus 2, f subscript minus 3. So and after you solve for all this, now we now get the value of our y subscript 1p, so which is now equals to 1.040838. So Miriam, please can you go to the next slide? So now, like now, what I said earlier, in our correctors formula, there's an unknown that we have to still solve in order to proceed to insert our values to our correctors formula. And to solve for that unknown, which is f subscript 1p, we have to use our value of our predictor value that we got using our predictors formula, which is 1.040838. Now to do this, now we're also going to go back to our condition. That's why I'm saying that the condition given every question is very important, because that's the gateway in solving correctly and not missing any, and not having incorrect values, which will lead to wrong answers. So now we're going to look at our condition again, which is f is a function of x, y is equals to dy dx is equals to x times y divided by 2. So now we'll just insert the value of x that we're given, which is 0.4. Because right now, what we're trying to do here is that we first try to solve using the predictors formula, which is also a solution. But the predictor and correctors formula work hand in hand, because the corrector formula depends on the value derived from the predictors formula and using the condition that was given for that problem. And the key thing to note here is that it's just the condition which must be followed and adhered to strictly. So now we're just going to insert our y1p and our x that was given in the question, which we are finding the points of y subscript 1, 4. So after we insert our y1p, then we'll multiply our x value divided by 2. So we'll get our f subscript 1p, which is equal to 0.208167. So after getting this value, now you can now proceed to insert all these subsequent values that we've been getting to our correctors formula to move us closely to the exact solution, which is the approximate solution. So Miriam, please can you go to the next slide? So now, using our correctors formula, now we can know that what we solve for now is the f1p that is close to the 9 here that we have. So we solve, after solving for it, all we just have to do is just to insert. So we insert our y naught, which was given in the question. We insert our h, which is our step size over 24. Then we now bracket 9 times 0.08167, which is our F1P that we solved for earlier. Then after that, we also take our previous F values that we've solved before even using our predictor's value, which is our F subscript 0, F subscript -1, and F subscript -2. So in the corrector's formula, we don't need the value of F -3 because it's not stipulated in the formula. So we just insert the values that we have in the formula and just solve. So after solving, we're going to get 1.041039. So you can now see that at the point of x1 is equals to 0.4, our y1 is 1.014039. So all this is still just our approximate solution. But what this method is just doing is that it's just moving us closer to the exact solution. So that's just it. So there's another example also. Miriam, please can you go to the next slide? So for this example now, we can see that it's a bit tricky than the last example, because for this example now we're given x is equals to 0, x is equals to 0.2, x is equals to 0.4, x is equals to 0.6, y is equals to 1.0214, y is equals to 1.091876, y is equals to 1.2221066. So now there's just a bit comma in this question, and the comma is that our initial value of y was not given, but we know already that the initial point of x is 0, which was given, but the initial value of y now is not given. So that's just the tricky part of this question, is that the initial value of y was not given, but it's just basically like what we already know, because at the initial point, x is 0, y is 1. So now you can look at our condition now. F is a function of xy is equals to x plus y minus 1. You can see the condition for this question now is different from the other question condition, which was x times y divided by 2. But here, the condition given to use to solve is x plus y minus 1. So may I please...
Excuse me, please, before you
Yes,
go
sir.
further. Now you
Yes,
have
sir.
given that function f of x comma y is given as that.
Yes,
Now
sir.
you now said y naught is not given.
No, the initial value of y is not given.
And that's y naught
Yes, sir.
is not given.
Yes, sir.
Now am I supposed to differentiate all these x, 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 x? Those are the stepwise movement. Is which one is the x naught, which one is the x1, x2, x, or x minus 1, x minus 2, like that. And am I
Okay.
supposed to assume that y, which one is y naught, which one is y minus 1, like that?
Okay, sir. Like following the rules of following the rules, which the first rule is that at any given point, the initial value of x is 0 and the initial value of y is 1. So when we are solving now, since it was not included in the question, but it's a basic fundamental rule. So I'm going to just insert the initial point of y, which is equals to 1.
Okay,
Now,
I get that, sir. My question
yes,
is
sir.
this: you have how many values of x? You have 4.
4 values, yes, sir.
How many values of y?
We have 3, sir.
So you assume that your y naught is not given.
Yes,
So
sir.
when you put your y naught up there, it means that your y equals 0 is also a valid point.
Sorry, sir, can you come again, sir?
All right, let me explain my thought. You have x equals 0, x equals 0.2, x equals 0.4, x
Yes,
equals
sir.
0.6. Those are 4 points.
Yes, sir.
Right? Then you have y equals 1.0214, y equals 1.0918796, y equals to 1.222 10646. That's 3.
Yes, sir.
Now, you said your initial point for x is 0, right?
Yes, sir.
Now, let's do a mapping, a simple mapping. So let's start from x is equal to 0.6.
Okay, sir.
So let's say that is our x minus 3, right?
Okay, sir.
Which tallies with y minus 3 equals 1.222 something, right?
Yes, sir.
Now look at x equals 0.4. It tallies with 1.09188, right?
Yes, sir.
Now x equals 0.2 tallies with y equals 1.0214.
Yes, sir.
So that means you assume that I think you should put something like a y up there and give it a question mark.
Okay,
So
sir.
that I do not assume that your initial assumption is that initial point of x is always 0, initial point
Yes,
of
sir.
y equals to 1. What about
Yes.
if the initial point is overruled and I give you that x naught equals, no, let me not say x naught, x equals 0 point something and y equals to 1 point something. Mr. Olumi,
Okay, sir.
please stop your video. Your chest, all right, thank you. So I think you should put y equals an asterisk or a question mark so that we know that the initial point is not given, or probably just want to make it tricky anyways, so that at least you know that always x equals 0, y equals 1 as the initial, as the starting point.
Yes, sir. Yes, sir.
Right, so continue, please.
Yes, sir. So according to the article and video I got this question from, so the way it was explained, it was said that there are some times that the person that said the question in mind might want to just test our technical know-how about the topic. So for someone that just knows the formula now without really understanding what the topic is, we have an issue with a question like this, because the four values of x were given, y 3 values of y were given. But for someone that has a deep knowledge of the topic and understands what the topic is about, we will always know that, okay, we have initial points, and at every initial point, x is equals to 0 and y is equals to 1. So the next slides, I'll be explaining further. Miriam, please, can you go to the next slide? So like now here, you can see what I was saying earlier. So here now in this question now, we're also not giving our step size, and we're also not giving our initial point of y also. So now to solve for all this now, so we have to go back again and use our condition like what I've been saying earlier. But now you can see that at the past value of x subscript minus 3 is equals to 0, y subscript minus 3 is equals to 1. This is our initial point of x and y. So at another step of x and y, x subscript minus 2 is equals to,
Hello, sir.
Yes, sir.
Yes. Why do you have to make x subscript minus 3 to be initial condition? Why not x not?
Yes, it depends. Like I've seen cases where sometimes they even connect some of these past value as yn plus 1, yn plus 2, yn plus 3.
Okay, so that is your own stylistic.
Yes, sir. Yes, sir. Just to make it simple, more simpler.
All right, but it may look confusing because when we start from y not, we expect, okay, I think it's right. Which is higher, -1 or -2? I think
minus 1,
is
sir. Yes, sir.
So you have -3 is smaller, -2 is greater. X naught. So when you have x naught to be 0.6, then it's confusing. That's issues. I don't know. I'm trying to be corrected anyways.
Basically, sir, according to my little knowledge about this topic, what I've seen, like the representation of the x and y values does not really matter based on my own understanding, because what just matters is that just using to just denote the past values that we're solving for. So some people might just go and say, okay, so of x minus 3, they can just denote that x n plus 3 is equals to 0. Why some might just denote as x minus 3? So it just depends on representation actually. So
All right, you may continue.
okay, sir. So like you can see here now, we've gotten our past values of x and y and also our step size, which is the difference in the increase, in the proportional increase of our x value. So now let's start calculating for our f minus 1, f minus 2, and f minus 3, and f naught in our formula. And to do this now, we have to go back again and use our condition, which is very important. So can you go to the next slide, Miriam, please? Now, our condition is f is a function of x, y is equals to x plus y minus 1. So that's the condition we'll be using in this question, in this scope of this question, because that's the condition that was given. So the condition is a very, very, very important thing to take notes when solving using the predictor and corrector formula. So now we can say to compute our f subscript minus 3 is equals to the value of x minus 3 plus the value of y minus 3, then minus 1, which was given in our condition. So if we solve for this, is equals to 0. So if we want to solve for f subscript minus 2 also, we also do likewise also. The value of x minus 2 and y minus 2, just insert it to our condition and solve. So do likewise for f minus 1 and f naught also. Then after getting the value of our these values, so now we are just going to just like we did for the other question, just to insert this value to our predictor formula and solve. Miriam, please can you go to the next slide? So now using our predictor formula again, like we already know now, y naught plus h, which is the step size, divided by 24 brackets 55 f subscript 0 minus 59 f subscript minus 1 plus 37 f subscript minus 2 minus 9 f subscript minus 3 brackets. So basically, all we just have to do here is to just insert the values we solved for in our previous slides, which are f naught, f minus 1, f subscript minus 1, f subscript minus 2, and f subscript minus 3. So when we now insert those values now, we now get our predictor formula value, which is our y subscript 1p. And the value is 1.42535,975. So now, like our, we have to get the value of our f subscript 1p. So to get that value now, we have to also use our condition that was stated in the question. Please can you go to the next slide, Miriam? So to solve for this now, like what I said earlier, use our condition. And what's the condition? The condition is f is a function of x, y is equals to x plus y minus 1. So we will insert the value of x, which is 0.8, because 0.8 is because the purpose of using this method is that we are asked to find the value of y at the point when x is 0.8. So now all we just have to do is just to insert the value of 0.8 that has already been known. Then also insert our predictor formula value that we got in our next slide, in our previous slide, sorry, then which is 1.42535975. So we insert all this to our condition and to now give us our f subscript 1p. So we'll now use this value now and insert it to our corrector formula, so our corrector's formula. So this using our corrector's formula now. So like this is the formula y subscript 1c, which denotes the corrector, then y naught plus h divided by 24 brackets 9 subscript 1p, which is the value that we solve for after getting our predictor's value. plus 19 f subscript 0 minus 5 f subscript minus 2 plus f, no, so sorry, minus 5 f subscript minus 1 plus f subscript minus 2. So what you just basically have to do is just to insert. So I believe after following the condition that was given in the question, this is the most easiest part of solving if you can remember the formula. Because all you just have to do is just to basically just insert the values and solve. So after solving, after we've insert our step size and the values that we've gotten using our previous computations, using predictor formula and our condition. So we now have our final approximation of y at when x is 0.8, which is 1.42552788. So at this point, if there's any question from anyone, if anyone has any question before my other colleague takes over, Ebenezer. Okay, since there's no question,
Good afternoon,
Ebenezer,
everyone.
take over. Okay.
Okay, thank you, Moses.
Okay.
Good afternoon, everyone. Good afternoon, sir. My name is Ebenezer, and I'll be talking about stability and convergence. Stability and convergence. So before I go on, I'd just like to beg pardon to be a bit fast because of the time that we have now. So I may not be able to do the 1+1s in all those examples. We'll just look at them, and I guess it's quite simple to understand. But basically, we'll be passing the knowledge, and hopefully we'll get the knowledge or the basic knowledge around these concepts. Okay, so we're talking about stability and convergence. About numerical methods of solving differential equations, and when we find out that the differential equations are too difficult, or the solutions cannot be gotten from the basic solutions, the basic ways of solving differential equations, then we approach them using a numerical method that tends to approximate the solutions so that we can get something close to what we already know that the solution will look like. Okay, so stability, a numerical method for an ordinary differential equation is stable.
Hello.
Yes, sir.
Yeah, are you watching football? Because I can hear some noise somewhere.
No, I think somebody's mic is on.
Yeah, please, if you're on this side, just mute your mic so that you can be able to sing very clearly. Thank you.
Lara Farouk, please turn off your mic. Okay, so can I continue, sir?
Yes, please.
Okay, all right. So a numerical method for an ordinary differential equation is stable if a small perturbation does not cause the numerical solution to diverge without bounds. So what this just tells us is that if the numerical solution gets close to the exact solution as time progresses, then we can say that that solution is stable. Okay, so for ordinary differential equation, when the equation, or when the solution progresses, we have that the curve will always approach zero. Okay, some of the factors that have stability are the differential equation being solved. There are some differential equation, no matter how you approximate or you solve them, you are going to yield errors. And of course, when there are errors, it will just go away from the exact solution. And the numerical method than other numerical methods. Okay, and also the step size, that's the h, Of course, my colleague Miriam has talked about what this H represents when she was talking about Euler's method and also from the Kutta method. Okay, Miriam, please let's go to the next slide. No, go back. Okay, so consider the first order differential equation with the initial condition given. That's y of t naught equals to y naught. All right, so that's the solution to the first order differential equation there. Y prime or y prime equals to lambda y. That's the first order, differential equation. Y prime equals to lambda y. Okay, so lambda, as we know, can be any real or imaginary value. Now, this solution will be stable if and only if the real values of lambda is less than or equal to 0. Okay, so because we already know that for a first order differential equation, when we plot the curve on the graph, we find out that the curve will always tend to 0 for each next value of the solution. So the curve will always approach 0. So to get that stability for any other differential equation that we may be faced with, okay, so that whenever it's going to be close to 0. So if lambda is positive, you can say that that solution will be unstable because will just keep on getting bigger and bigger as time progresses. Okay, please, the next slide. Okay, here we have an example. All right, so let's consider the analytical solution to the first order differential equation. Now we have that the exact solution has been solved. Okay, so we know how we go about getting the exact solution, where we integrate the differential equation and also do our mathematics over there to get the solution. So the solution here is what? Y equals to y naught e raised to power, that's the exponential of minus at. Okay, y equals to y naught e raised to power at minus at. So what this tells us is that if as time progresses, if the time, when time progresses, it tends to become infinity. So as it goes bigger and bigger during the numerical method, we find out that okay, the y naught will tend to 0, we tend to approach 0. Okay, so the solution will always tend to approach 0. And that is what we have been saying, that okay, when we plot that on a curve, we find out that from various examples, from various differential equations, first order differential equations to be precise, the y will always approach 0 whenever it's plotted on the curve. So that solution will be stable. So that's just the exact solution. That's the true solution to the first order differential equation. Now, we're using Euler method, which is a numerical method to find the solution for first order differential equations. Okay, so when we are using this numerical method, we have at the back of our mind that we do not know the actual way, or we do not know the actual solution to that equation at that particular point in time. So that's why we want to solve it using the Euler's method. Okay, so from the previous slides, or from the previous topics that we have considered, we've talked about the Euler's method, and Miriam has done due diligence. So we can find out that yn plus 1, which is our next value of y, is always equal to the previous value of y plus the h, which is the step size, and the function of, multiplied by the function of x and y, which is the derivative of that particular solution. All right, so when we do the mathematics, we find out that yn plus 1, okay, will be equal to yn into bracket 1 minus ah, if we have to, because we are considering this solution here by your left hand side, you have dy dt equals to minus a. Okay, so when you substitute the value of a into that solution, or into the method, the Euler method, we have that yn plus 1 equals to yn into bracket 1 minus ah. All right, so for a stable solution, okay, we always want that the next solution will be very, very close to the previous solution. So that's how we have that yn plus 1, the absolute value of yn plus 1 will always be less than 1. So if we want that solution to be close to the previous solution, it has to be always has to be less than 1. Okay, and if that is less than 1, from that equation, we can find out that 1 minus ah, that is 1 minus ah. If you look at that equation there, yn plus 1 equals to yn into 1 minus ah. Okay, so if you do yn plus 1, if you divide both sides by yn, all right, you have that yn plus 1 over yn will be equal to 1 minus ah. So if we are saying that yn plus 1, the absolute value of yn plus 1 over yn is less than 1, therefore means that we are also saying that 1 minus ah, okay, the absolute value has to be also less than y1 for a stable solution. And if we do the math, we find out that h less than or equal to, h is less than or equal to 2 over a. So that's the condition for a stable solution when we are solving the first order differential equation using the Euler method. So if the solution meets this condition that for every h it has to be less than 2 over a, which is always the coefficient of y in that particular equation, then we know that that solution will be stable. So when we're talking about the conditions for stability, we talked about the step size. Okay, so this step size really affects how the solution could be either stable or not. So this is the condition for first order differential equation. So there are other methods, but we are just looking at the Euler method for the purpose of this class. Okay, please, the next slide. Okay, so this is a typical example. All right, it says we should consider the first order differential equation below. Please, I'm sorry about the way I plotted my graph. My sketch is not really nice. I'm sorry about that. All right, so the first order differential equation, consider the first order differential equation below. Show when the numerical solution becomes unstable for step sizes h equals to 0.1, 0.2, 0.3, 0.4, and 0.5. Okay, when solving with the Euler's method. All right, so we have, that's the differential equation, y dt equals to minus 5y. All right, so and the Euler's method from the previous slide that we have seen, we know that yn plus 1, which will be the next solution for y, is equals to yn into bracket 1 minus 5h. Now, from the previous slide, we saw that yn into bracket 1 minus ah. So the h here can now be substituted. The a can be substituted for 5, can be said to be 5 here. So that's how we came about this solution here. All right, so considering for step sizes h equals to 0.1, 0.2, 0.3, 0.4, and 0.5 respectively. Okay, so taking h to be 0.1, all right, so our yn plus 1 will be, if we substitute the values there, will be yn over 2. Yn over 2. So what that implies is that, okay, for the next value, you know, when Miriam was explaining, she said that we always use the previous value to get the next value of y. Okay, so when we are considering these steps for this particular step size, all right, h equals to 0.1. For the next value of y, for every of that step size, h equals to 0.1, we have that y, the next value will be half the previous value. So if we plot that on the graph that we have by the right-hand side there, just by the side of the equation there, okay, we find out that the first curve that we have there is the blue curve, and that's just the curve that tells us the true solution to this particular equation. You can see that it's approaching 0 from 1 to 0, and it stops at 0 and continues going as time progresses. So it continues on the 0 line. All right, so now when we plot this particular solution that we have gotten now as yn plus 1 equals to yn over 2 on that particular graph, those are the red dots that you can find that has been connected together also. they are all tangent lines. Okay, so just connect them together to show them on the plot there. All right, so for yn plus 1 equals to yn over 2, find out that, okay, since the first initial conditions are y is 1 and the step size 0.1. So when we plot that yn over 2, that will be 1 over 2, which will be 0.5. So that's why we get the first dot at 0.5 there. Okay. And also, if you trace it down, you find that it's at the step size of 0.1. Okay. So if you continue on that step size of 0.1, so it means that for the next step, okay, it's always going to be half of the previous step. So half of 0.5 will give us 0.25, and you have the next dot there. Also aligning with the 0.2 step, because we have added another step, 0.1 plus 0.1. So that's how the tangent line continues, and we connect them together, and we can find out that it is approaching 0. All right, so that means that it is going closer and closer to the true solution as time progresses. So that's the condition for a stable method. So we are looking at the Euler method. So we can say that this Euler method is stable for this step size, h equals to 0.1. All right, so when we do that, the same way we do the other step size, because the question asks us to do other step size. So we do the other step size for h equals to 0.2, yn plus 1 equals to 1, put in the values 1 minus 1, and then we have 0. Okay, and then we'll plot that on the graph, and you can see that with the other the other line there, linking straight to 0, where you have the next value of n, which is yn plus 1 equals to 0. So it goes straight to 0 and it stops at 0. So what that implies is that for every next value of n, it's always going to be 0. So that's why you see that it just continues on the 0 line when you look at it from the from the x-axis. So it continues on the 0 line. So for the next value of y is always going to be 0 from that computation at that particular step. Okay, which is h equals to 0.2. So we do for h equals to 0.3, and we find out that our next value of yn plus 1 will be minus 0.5 n. Okay, so we have that on the other graph that is just below the previous graph. Okay, so we see that on the plot there. Now, okay, the plot is behaving like a waveform now. It's now oscillating, but even though it's oscillating, it's still stable at this point, because while it's oscillating, it's still approaching 0. Okay, so we can see the plot by the side there. Okay, it's still approaching 0, going closer and closer to the 0, even though it is oscillating. So at that point, we say that it is stable. And the same thing also happens for h equals to 0.4, which is not plotted here. For h equals to 0.5 also, we put in our values, and when we have yn plus 1 equals to minus 1.5 yn plus 1. Okay, and at this point, it is unstable, because when we plot that, we find out that it goes beyond the bounds of this particular plot. So it goes beyond bounds. So we say that it is unstable. And if you look at it, comparing it with the condition for stability, we find out that, okay, h equals to h is less than or equal to 2 over a, and a is 5. So 2 over 5 will be 0.4. Okay, so it means that if you are taking h greater than 0.4, that means that that solution will be unstable. So if you want a stable solution that will look like the true solution, then you have to take your step sizes for each iteration to be less than 0.4 for this particular differential equation. H is less than or equal to 2 over a. So that's the condition for a stable solution for this Euler or Euler method. Okay, please let's go to the next slide. Okay, now we are done with that. We'll go to convergence. Okay, so convergence, this tells us whether or not our numerical solution will end up representing the exact solution as delta t approaches 0. Okay, so as time goes on, okay, we find out that because of the errors that will be accumulating when we are trying to solve the differential equation using numerical method. Definitely there are going to be errors that will be accumulating because numerical methods are just an approximate method, approximate way of solving the original solution. So errors are going to come into play. Now, because of those errors, as time goes on, the errors may, depending on the differential equation being solved, may be increasing rapidly. So if we have that the errors are increasing rapidly, to distort that equation, to not make the equation look like what we think or what we thought that it would be. So that equation might not be convergent. Okay, so for a numerical method is convergent if the maximum error goes to zero as the time step goes to zero. So you can see that on the plot there. Okay, on the plot of V against T. All right, so the curve there is unknown, like we have said earlier. It's just the true solution is unknown, but due to our previous works, we know that every time that we solve a first order differential equation, it always looks like this. Okay, it goes down like that. The curve also, we just assume a curve of that shape. All right, and so when we are putting solving our numerical solution, okay, we are given V naught and T naught at first, so we can plot that and we can use that to project for the other values of V, the next values of V. Okay, now because of the numerical solution or the numerical method will always have some values of errors in it. So we find out that there's always going to be an error. So the error there can be calculated using the formula that we see there, Vn minus Un, the absolute value of Vn minus Un for every step. That's for every iteration, n equals 0, 1, until you get to the last step, the end step. Okay, so the error is calculated thus. Vn here just talks about the numerical method that we are using. The next value of the numerical method that we are using, that's the Vn. You can see that with the red dots that are there. Okay, so it goes on and on and on until you get to the last point where we are calculating for. Okay, so a numerical method is convergent if the maximum of a set of the iterative values from 0 to the nth term of the error, I've talked about the error, which is Vn minus Un, if it approaches 0 as time goes on, okay, as time goes to 0, as delta t goes to 0, sorry, not as time goes on, as delta t goes to 0, delta t is not, delta t is just the difference between the next step in time and the previous step that we are coming from. All right, so as the 30 goes to 0, all right, if the value of the numerical method that you used minus the exact solution, if it also approaches 0, then we can say that that condition, that numerical method that is being used will be convergent, will look something like the original solution. Okay, quickly, let's go to the next slide. So we have an example here. The example is to consider another differential equation which has the initial solution to the U naught equals to du dt. U naught equals to 1. The differential equation is shown as du over dt equals to minus u squared. Okay, so the question there is at time t1, show that the numerical solution is convergent when delta t, that's the change in the step sizes, is equal to 0 0.1, 0 0.2, and 0 0.4. All right, so the plot of the forward Euler solution for time 0 to 4 is given below. All right, so we can see the plot. And how do we come about the plot? We came about the plot. If you look at the right hand side where we have the initial condition to be 0, t equals to 0, and u equals to 1. All right, so we fit that into the original solution for the differential equation, where we have u equals to 1 plus t raised to power minus 1. So we solve that for at t equals to 0 and at t equals to 1. So we find out that our u will be equal to 1 over 1 plus 1 is 0.5 and still equals to 2. U equals to 1 over 1 plus 3 equals 0.35. So the table that we use to get the curve is there, is shown below. Okay, so when you plot that against each other, you find out that you get something like that. Okay, so we are solving the question now. They said at t equals to 1, we should show that the numerical solution is convergent when delta t, as the change in step sizes, equals to 0.1, 0.2, and 0.4. Okay, so we are using the Euler method again for this particular differential equation. All right, so using the Euler method, we find that the next step, which is un plus 1 equals to un plus change delta t function of un and tn. So if we impute our values at this particular step, okay, so this iteration step is n equals to 0, and we impute delta t to be equals to 0.1. We find out that we have that solution for u1, the next step, which will be 0.9. So please, the next slide. So like that, we continue with the other steps at delta t equals to 0.2, still at that first iteration step, and which is n equals to 0, and also at delta t equals to 0.4. So we get the solution for each step at that particular point. So when we plot that, we draw there's a table there that shows what we are doing. Okay, so when we draw that put that inside the curve, remember we already have drawn the curve of how the true solution looks like. Okay, so when we impute these values into the plot that we have, we find out that, okay, so when delta t was 0.4 from the graph there, we can see that u1 was 0.6, and also when the delta t was 0.2, you can see that u1 is 0.8 from the curve. Which is those where you have those dots there, that's what I'm talking about now. Again, also when you have delta t equals to 0.1, we have that u1 equals to 0.9. Okay, so those are the dots, and you can see it clearly that as delta t is decreasing, okay, it's approaching 0. All right, the next value of u is also going closer and closer to the true solution, which is the curve. Okay, so it's going closer and closer to the true solution at that particular time. We are talking about that when t equals to 1. Okay, so we can do that for the other time when t equals to 2 and 3 and 4, as many times as you like. Okay, just so that you can see the convergence method clearly shown there. So we can say that the worst case error, of course, we have talked about what the error is. And the worst case error E naught over here is equals to U naught minus E naught. Just simply tells us e raised to power n. We are talking about the first iterative value, n equals to 0. So that's why I have e raised to power 0 there. So it's equals to U naught minus U1. Okay, so we have that 1 U naught, which is the numerical method that we are being used, minus the exact true value, the solution, which is U1. Okay, so we have that 1 minus 0.9, and we have 0.1. So we'll do that for the other values, and we get 0.1, 0.2, and 0.4. So as delta t is going to 0, we can find out that the error is also going to 0. It's also approaching 0. So as the error is reducing, because as delta t is going to 0, so u1 tends to look like the original curve, for all cases of n. So for this particular method, at this point in time, we can say that this method looks to be convergence. Okay, it's converging, like representing the original curve that we have over there. Okay, so quickly let's go to the next slide. All right, so that's that about convergence. Okay, there are other methods that we can talk about, but due to time and of course, like what Miriam said, complication of the Kutta method and other things like that, we just stick to the Euler method for this stability and convergence. So we are looking at the next topic, 2-point boundary value problem. Okay, so a boundary value problem is a differential equation together with a set of additional restraints called boundary condition. Okay, so you have a differential equation, and of course you have other restraints that are called the boundary condition. The solution to a boundary value problem is a solution to the differential equation which also satisfies the boundary condition. So you put the boundary condition side by side with the differential equation, because when you get the differential equation, you solve for the various conditions like we have been seeing. We've been having only just one initial value for the condition before, but for a 2-point boundary value problem, we have two initial conditions. Okay, so we'll see that when we consider the examples that will follow in the following slides. So a differential equation together with two suitable boundary conditions form a 2-point boundary problem. So you can see that represented in the equation below, where you have y prime prime plus y for p into x, p a function of x, y prime plus q x y equals to g of x. All right, so y at beta equals to y naught, and y at alpha equals to y naught, y at beta equals to y1. So those are the initial conditions. There are 2 points, y naught and y1. Those are the initial conditions. From the other ones that we have been saying previously, you'll find out that it was only one that we have been talking about, but for this one we have two initial conditions. So where p of x, g of x, and q of x are all functions of x that may either be constants or variables, depending on this differential equation that we are looking at per time. Okay, please let's go to the next slide. So we say that if the function of g of x has the value of 0, and the boundary values also y naught and y1 are also 0, they will say that that equation that we just seen is homogeneous. Okay, otherwise the problem is not homogeneous. And homogeneous problem usually results in solutions that are often called trivial solutions because of how easy you can get to the solution. But if we have that y naught and y1 and g of x are not 0 values, then we can have a non-homogeneous value, which will imply that the equation that will be solving at that particular time will be complicated. Okay, so that's just the representation of what we said just now. We have y prime plus p of x and that over there. Okay, so initial value problems, IVP, and boundary value problems, BVP, appear to be quite similar. So initial value problems from the onset of the presentation where we saw the Euler condition. Okay, that's where we have one boundary condition. But now the boundary problem, we have two boundaries similar in some ways. Okay, while initial value problems are always unique, that means you can always have a solution for initial value problem. Boundary value problems, the solutions may either be unique, they may have no solution at all, and they might have an infinitely many solutions. Okay, just tells you that this kind of boundary condition may tend to be complicated. All right, so let's go to the next slide, please. A good way to tell value problem is that for initial value problem, the initial condition has one part in the function of y and the other in the function of y prime. Okay, so that representation is there for you to see. I think there's nothing to explain here. Please let's go to the slide, the example. Okay, so for us to solve examples on initial boundary value problem, we have to have a background knowledge of how to solve second order differential equations. Okay, so that we have these second order differential equations coming up here. Okay, So we have that for second order differential equation, which is always written as that. That's the standard form: P of x y prime prime plus Q of x y prime plus R of x y equals to G of x. Okay, so the method or the algorithm that is always followed, you always introduce an auxiliary equation, okay, so that you can get the roots of the equation. That's why we introduce the auxiliary equation. And then the y that we see over there equals to e raised to power rs is an assumed general solution when we are talking about second order differential equation. Okay, so we can get our y prime and y prime, which are the first derivative and second derivative. I think we have talked about that at our last class. First derivative, higher order derivative. Okay, so we get that from that differentiating the e raised to power s. We have r e raised to power rs. Differentiating the second time, we have r square e raised to power rs. So when we substitute that into the original equation, we have that a r square e raised to power rs plus b r e raised to power rs plus c raised to power rs equals to 0. And then we factor out e raised to power rs. We have that solution over there. And then also, when we divide both sides by e raised to power x, okay, we have that solution over there. Okay, so the roots of the equation can be gotten, because when we look at it, it looks like it is a quadratic equation. So there are ways to get the roots of quadratic equation. You can either get by factorizing or
Yeah, is the fellow still presenting? Can't hear him again.
using the almighty formula which is written there. So the general solution can be, it depends majorly on the roots, two roots, and there are. Hello, sir.
Yeah,
Hello,
you may
sir.
continue. I didn't hear you at the time.
Oh, I'm so sorry about that, sir. Probably it's network. All right, so we are at the root of this quadratic equation. So the general solution conditions are is that if b equals b square minus 4ac is greater than 0, you have that, okay, so that's roots are real. So for that kind of roots, we have that the general solution will be y equals to c1 e raised to power r1x plus c2 e raised to power r2x. Let's c1 and c2 are just some constants that will look that we will have to solve for when we are dealing with such examples. So that we can get the unique solution for that particular equation. Okay, and also if we have equal roots, that is b square minus 4ac
Yeah, I think you need to
is two
change your
equal roots
position. You
is
need to
y equals
change
to
your
plus c2 x.
hello.
Yes, sir.
Yeah, your stuff is just crumbling and wobbling. I think you need to change your position to get a good signal.
Okay, so is it good now? Hello, am I audible now?
You may
Hello.
continue. You may continue.
Okay, sir. Okay, so we're talking about the equal root solution. Of course, we have that y equals to c1 e raised to power rs plus c2 x e raised to power rx. Okay, for the last one where we have imaginary root, that is b square minus 4ac is less than 0. We have two imaginary roots. We can say that our solution will come when we use y equals to e raised to power alpha x c1 cos beta x plus c2 sine beta x, where the roots of the equation are alpha plus or minus beta I, which is the imaginary value. Please, let's go to the next slide. Okay, so let's solve an example. All right, so we have that solve the boundary value problem y prime prime plus y equals to 0. All right, at the initial conditions, y at 0 is 0 and y at pi over 2 is equals to 0. So the solution, of course, we have the second order differential equation. We rewrite that solution just like that, okay, and also bring in the auxiliary equation there, ay prime prime by prime, and we solve the equation that comes out of it. That's r squared plus 1 equals to 0. And then for this particular solution, we find out that we have imaginary roots. Okay, so when we have imaginary roots, we use the solution y of x equals to e raised to the power alpha x c1 cos beta x plus c2 sin beta x, so that we can solve for c1 and c2. Okay, so alpha and beta can be known from the roots of the equation over there. So alpha is 0 and beta is 1. All right. So at the first initial condition, x equals to 0, y equals to 0. You can see that from the question there where we have y of 0 equals to 0. That's the first initial condition where we have y of 0 equals to 0. So x equals to 0 and y equals to 0. So y at 0 equals to e raised to the power 0. Of course, s is 0, so anything times 0 is 0. And then c1 cos 1, we just put that, plug the values of all the things that we have been saying earlier. So when we get that, we find out that c1 equals to 0 and x, the other condition, x at pi over 2, x equals to pi over 2 at y equals to 2. So we also plug that into the equation there, and then we get c2 to be, okay, c2 to be 2. So when we have gotten c1 and c2, putting that into the differential equation, the solution, the general solution to the differential equation, right? We have that e naught e raised to the power 0 times x, 0 cos 1 x plus 2 sine 1 x. If we do the math, we have that 2 sine x is the general solution. So it is unique as general solution for every y at x instances, okay, for this particular problem. So let's go to the next example. So the next example, similarly, we are asked to solve the boundary value problem with y at 0 equals to 3 and y at 1 equals to 7e. All right, so we write out the problem. That's the differential equation there. Y prime prime minus 2y prime plus y equals to 0. Put in the auxiliary equation and then solve the quadratic equation and then since we find out that we have 2 equal roots when we solve that equation there. 2 equal roots. So for equal roots, the condition is that y of x equals to c1 e raised to the power rx plus c2 x e raised to the power rx. So from the first initial condition, y at 0 equals to 3. All right, so we put that into the equation. We have that c1 equals 3. All right, so also we put that, we look at the second condition where y at 1 equals to 7e. All right, so we do that, 7e equals to that equation. All right, and we get our c2 from there to be 4. All right, so we can rewrite the general solution for this differential equation, which is also a unique solution, as 3e raised to the power x plus 4x e raised to the power x. So at this point, we'll be drawing the curtain on today's presentation. I want to thank my colleagues, my team members, and also everyone for listening. And thank you, sir, for the opportunity to learn and also present. So we'll be stopping here. If there are any questions, we can go through them. Thank you.
Right. Do we have questions from the audience? Questions, please.